Hi all, welcome to today's seminar, which is organized by the EuroCC2 project. EuroCC2 is a pan-European project with more than 30 countries participating. The goal of EuroCC2 is to enhance the competencies of Europe in advanced technologies like HPC, machine learning, AI, and high-performance data analytics. Today's seminar is entitled Machine Learning for Agents and Multi-Agent Systems, and is given by Professor Maria Klee, reader in Applied Artificial Intelligence and Robotics, Aston University, Birmingham. Professor Maria Klee is a director of Aston's Computer Science Industry Club, driving application of cutting-edge research in collaboration with the industry. Her research focus lies in the intelligent agents and multi-agent systems. Her core work involves modeling complex systems and optimizing them through the fusion of multi-agent system techniques with machine learning and deep learning. Let's now welcome Dr. Klee on the floor.
Thank you very much. Hello all, thank you for having me here. My name is Maria. As Kyriaki said, I work in multi-agent systems, agents and multi-agent systems, pairing them up with machine learning. I'm currently at Aston University, which I joined back 17 years ago. And before that, I was at Imperial College, where I did my undergraduate in computer science and stayed on for a PhD in intelligent systems. So agents and multi-agent systems. In this area, we use intelligent agents to represent decision makers that act strategically to achieve a goal. Think of these agents as maybe Alexa or Siri, or the intelligence of a robot, or the intelligence of an autonomous car, or even a human decision-making that we model to be part of a society or an economy. Sometimes we study this individually, one by one, and we try to optimize their behavior. Sometimes we go for analyzing the whole system they inhabit. So we are often working towards optimizing the environment, optimizing, defining the rules of interactions, or defining the agents, the intelligent agents themselves. And these are the three areas, I would say, the three strands of work that I like to do. I like to simulate complex systems and trying to understand the dynamics and the overall emerging properties. I also work in, I think your colleague is experimenting a little bit with the screens over there. I also work with online continuous learning and transferring learning of previous experience to current experience for intelligent agents and mechanism design. So we're going to be revisiting this slide quite a bit. I'd like us to start with mechanism design. It's a key interest of mine. And if you haven't heard the term before, is the area of AI where we try to find out which is the optimal set of rules that we need to apply in a particular encounter so that it exhibits the properties that we want. It could be perhaps choosing the right election system for a particular problem, or the right auction, the right negotiation protocol. I'm particularly interested in working on mechanism design in settings that are dynamic, that keep changing, such as volatile market scenarios or dynamic supply chains, that we need them to be agile and be resilient to the fact that participants come and go, or their capacity changes unexpectedly. This is the first project of mine that I'd like to talk to you about. This is decentralized supply chain formation in an uncertain environment. I was talking to some of you this morning, and I was saying how when I was doing this work, But around 2012, 2015, it felt entirely theoretical, not to me, but to all those people that I was trying to convince. So this is all about having an automated mechanism that allows supply chains to be formed on the fly, allows companies to join and companies to leave the supply chain, allows them to change their capacity, what they offer to the supply chain. And not many people were interested at the time. And I was using this fashion example of apparently, if a model hits the runway wearing a particular outfit, or if they go to the Oscars wearing a particular outfit, there's a mad scramble for the Zaras and the H&Ms of this world to bring a copy of that outfit to the high street within 2 weeks. It's true, but not many people are interested in that. But then COVID came with all its evils, but I was vindicated, because then we saw how much we need those agile supply chains. Because it turns out very often the market changes its needs. And what you see there, the supply chain, the network of businesses and so on, and you see, well, you would see. Do you think so? My connections? I'll keep holding. Okay. So you see there, two competitors, Ford and General Motors, really relying on the same suppliers. And that's how it is in the world. This is a very simplified supply chain, but we found out, all of us, during COVID, how we all go back to the same suppliers because we rely on centralized supply chain formation. The way the market is, there is a need for agile procurement, and we need to be able to form new supply chains, the most efficient possible supply chains, quickly, and be able to adapt them or let them adapt organically. So the problem of automated supply chain formation boils down to, I keep holding. Yeah, it does work. No? Who do we trade with at any given point? Who do we partner up with? So the traditional approach is very centralized. There's companies out there in the world. What people don't know is that DHL, for example, is one of the most active mediators of supply chains that are set up by these centralized parties. They're slow, they're prone to human error, and of course, prone to bias. So it's important to be able to get rid of the middleman, get rid of these mediators, and be able to form our supply chains computationally, efficiently, in an automated way. So the tradition is centralization. The state of the art when we started, when it comes to decentralized, is to have bipartite auctions across the producers and consumers, which works, but it has certain limitations to do with computation and an upper bound in the efficiency. I'm showing you here a simple task dependency network, which is the formalization that's used to study this. So it's an artificially simple supply chain. The squares, the rectangles, you can follow them across the screens. They are the producers or consumers. And the circles are the goods that are being exchanged. The arrows show potential flow of goods, so who you can buy from, who you can sell to. And the little numbers are how much it costs to produce, or how much value do you gain from consuming a good. There's other things that we consider, those blue crosses that you see there, that for simplicity I haven't included here, but they are particularly important. That lines the capacity of production of a particular factory and so on.
I'm not promising to help.
But you can feel free to try, yeah.
Isn't that a really good with resolution issues? Let me see.
Λοιπόν, ένα λεπτό να δούμε εδώ. It's different Mac version. System preferences, display. Yeah.
I don't think it's the cable.
Just a second, because maybe.
Μπορούμε λίγο.
Is it okay now? Which is the
Can
problem?
you try to?
Okay.
Let's see. Slideshow, current slide.
Konstantine, viewing this from the internet, it is fine. It
Mm.
changes. There's no problem viewing it from my laptop through the internet.
Yeah,
I think it has to do with the compatibility between the projector and the resolution that this exports.
So
right?
let's look at the resolution again then, maybe. So this one, right? Color, arrangement, display. Should we go scaled? Maybe.
Kind of scale. Τι θα
Ας
αλλάξουμε?
το βάλω εκεί πώς ήταν. Ένα λεπτό. Pressure display. Θα κάνω disable τα notes.
Ναι,
Ναι.
έτσι. Και να πάμε στο close slideshow. Λέγω να κάνει διαφορά.
Ναι. Να κάνουμε disable να βλέπω. Όχι.
Μία.
Όχι.
Α, είμαστε πάλι στα notes.
Ναι.
Πώς βρεθήκαμε.
Εντάξει.
Έγινε. Εντάξει, ευχαριστώ πολύ. Ευχαριστώ. Ναι, νομίζω ναι. Well, let's try anyway. So this is a task dependency network. This is the way that we formulate the problem, really. The arrows, remember, show what's possible, the potential flow of goods, not the agreed one in the end. And the point is to find the subset of this network that maximizes the value of the allocation. And the value of the allocation is the sum of the consumed value minus the sum of the producer's costs. So for these numbers, one optimal allocation for this simple network is the one that you see there. That producer one sells good one to producer three, and producer three then makes good three, which is consumed by consumer one for these particular values. So this is the aim. This is where we want to reach. Now, in reality, the networks look much more convoluted than I've shown you. And in reality, the biggest problem is not really the number of nodes or the echelons of the supply chain, but the presence of cycles. in the supply chain. And we consider cycles without looking at the direction of the arrows. So huge has several cycles there. So instead of determining allocations using auctions, remember what we're trying to do here is to form the supply chain in a decentralized way. And auctions was the state of the art in decentralization at the time. We use something called loopy belief propagation, which you may have come across before. It's by Jutia Pearl in 1992. Now, with this problem, with this method, you have the producers and consumers exchanging messages, and in its purest version, the loopy belief propagation guarantees to converge to the exact solution on acyclic graphs. It provides approximate solution for graphs with cycles, even though technology has become quite a bit better since. Excuse me. So here's the process. Here's what happens. We run loopy belief propagation, and at each iteration, each agent, whether a producer or a consumer, passes a message to each of its neighbors, and the message contains a vector of beliefs about which state the neighbor should be in. So let's think about that. Let's talk about states first. So in this simple network that we're using as an example, producer 3 can be in one of two states. They can be either inactive, or they can buy from P1 and sell to C1. And C1 in its turn has three possible states. It can be inactive and either buy from P3 or buy from P4. This is the very simple case where you can buy only one unit. In reality, there's more states where you can buy a combination of units, some of one and some of another, some from P3 and some from P4. Now, remember in our messages that we exchange beliefs about the state. So beliefs encode how much it costs to be in a particular state. So for example, if you're stuck in a state that's incompatible with that of your neighbors, then that entails a huge cost. If you, for example, end up producing lots of goods that your next person in the echelon doesn't buy, then this is a bad combination. That's it entails a lot of cost. So in loopy belief propagation, we exchange those messages with then at the end of each round, the intelligent agents update their beliefs according to the messages they have received, and they continue sending more messages and so on. So this message passing phase goes on for as many iterations as needed until at some point convergence is reached. Which means that agents for the past X amount of time have been holding stable beliefs about the cost of states and what they should be doing. At this point, we allocate the contracts and we decide what the supply chain should be. We can continue, however, message passing to allow for the supply chain evolving with time. For example, deadlines changing, capacities changing, new players coming into the market, and so on. Again, the way that we decide the costs of things is to do with the value of the allocation. Now, this has brought about some unexpectedly good results in comparison to the auction-based approaches. So it converges faster across all the network types that we've tested, and it significantly outperforms the auction mechanisms. To give you an indication here, when we are comparing like for like, because ours can do a lot more, on the left-hand side, you have some networks that are used in this field as benchmarks. And we know we run for 100 different versions of each network with different values, different capacities, and so on. And we achieve optimal, which optimal really you cannot guarantee unless it's centralized in the majority of the cases, and near opt and in 100% of the cases for the majority of the networks, and very high optimality for even the hardest, like gritty bad, which is one with many cycles. So in the second and third row are some auction-based approaches. And this has given us then momentum to move on to harder and harder problems, which I'm not going to cover here, harder networks, and also areas which the auction mechanisms could not even think about trying, as in continuing agile procurement after the supply chain has been formed, to find alternative formulations to account for the dynamic nature of the landscape. What I'm particularly proud about is that then this methodology has been taken and is being applied in other areas, totally different to supply chains. For example, it's being used in deployment of teams, let's say for addressing an emergency scenario. So sending out the ambulances, the fire service, and so on, in particular in different areas if a city is being attacked, let's say, which again, they were being in the past only dealt with through auction procedures. So even though this is a little bit earlier work, 2015, I think was the last paper, only last year, I was asked to give an interview to faculty.net to explain it, because it's being used increasingly since COVID and that big ship being stuck in Suez. Made us realize how we need to be more agile about our procurement. A lot of this technology we've also applied to these three companies that you see there, Obilex for formation of credit chains to finance large-scale projects. These are a little bit like supply chains. And Remilia, who was then bought by Blackline for prediction of timeliness of future invoice payments. We've received a substantial grant by the Royal Society not too long ago, and we're extending this work for gradual budget feasible procurement, which means you delay forming your supply chain until the last moment to make it, more versatile. And it's the only one that's not assuming, the only technology that's not assuming the trustworthiness of providers. So this has been my mechanism design project that I wanted to share with you. And I'd like to move on to online and transfer learning. There's a lot happening in this area. And in agent systems, we are very interested in using the data that's currently available to make decisions in the moment, not necessarily rely on historical data to do some analysis. And we have had some very interesting work here. I wanted to first talk to you about our energy broker and agent. Has anybody heard of the PowerTAC competition? The PowerTAC is a competition in agent-based systems. We really like our competitions in this field, where the aim is to create a broker that buys energy wholesale and sells it in the retail market. You have those brokers competing against one another. The winner is the one that makes the most profit. And our broker, all these brokers in the competition, live in an environment which is entirely real. So you've got all of the parameters of the power, of the energy market. You've got the weather, the cost of storage of energy. You've got different versions, different types of energy. You've got solar power being sold back to the grid. You've got everything that you can imagine there, electric vehicles. At the time when we started participating with Aston Tag, our agent, it was thought that simultaneous optimization of your retail and your wholesale strategy in PowerTag is totally intractable. So people were winning the competition at that time by either focusing on one or the other, or focus for 5 minutes in the one and 5 minutes in the other, and so on. We were the first ones to introduce reinforcement learning in this particular domain. Set of brackets here, reinforcement learning is the type of learning where your agent is learning how to act on the task through experience, without an explicit teacher, without having access to previous data necessarily. So the agent is sensing the environment. It has a way to interpret the environment state. It decides how to act upon the environment, affect it, change it, and then reach the new state and receives a reward based on how good the effect was. The goal of the agent and the way it learns is that it needs to maximize, it learns to maximize the cumulative reward it receives over time. So in this, we were the first ones to introduce reinforcement learning. And for the first time, we were able to optimize the retail and wholesale strategies at the same time using semi-Markov decision processes, which we solved with HRL, hierarchical reinforcement learning. So our architecture looks something like this, where you have multiple MDPs, and you have multiple, sometimes conflicting goals. So at one point, the left-hand side, the option customer enticing, looks at optimizing the market share, whereas the right-hand side is going for higher profit. And each of those has MTPs underneath it, one for the retail, one for the wholesale market. So the agent buys wholesale, it sells retail, it needs to make decisions for both. So with time and enough experiences, the agent learns how to behave, and we won that competition. But what's more than that, we found out that this architecture that we've built here can be transported as it is in a completely different competition, the supply chain formation competition, where you have an agent that buys wholesale parts and creates computers for the retail market in real time for very volatile market settings. And what we found is that if we trained our agent in one of those competition environments, let's say the supply chain competition environment, and deployed it in the power trading, it did much better than if it was trained on the environment that it was going to be deployed. So this is the performance, what we see there. On the right is the number of games, so the experience of the agent against the profit that it makes. If it's trained in the same environment, I think this is the PowerTag environment. You see the blue line, this is how much profit it makes and how it goes up over time. The green line, however, is our agent that has been trained in the supply chain task being deployed in the power trading task. It starts higher up. It gives it bootstrap advantage to its performance, but it also continues to learn much faster. Now, this whet my appetite. I wanted to do more transfer learning after that. So we started, it was the same time as there were some headlines around beating world champion at Go with deep reinforcement learning. So we thought, and we had experience, that with the traditional RL that we were employing, we needed a lot of environment interactions, a lot of trial and error, which is costly, and it could be costly in a competition like this. We wanted faster decision-making, and we wanted to avoid handcrafting our interpretation of the state. So we got rid of that, and we went for deep reinforcement learning, where we take the state raw as it is from the environment. We did some work in Atari, transferring from one game to another, which did very well. But we sadly don't have time to talk about this today because I really, really want to talk to you about our traffic work and how we deploy deep reinforcement learning and all the rich data sets that we have in vision data sets for traffic to do smart traffic management. So what we do here is that we control traffic lights based on already available CCTV footage in real time. Of course, this is receiving, because of the topic, because it's AI, it's receiving a lot of attention. So we've got the BBC and Deutsche Welle and so on, Radio New Zealand, do pieces on this work. What I like is that it's really rather simple. So we have CCTV cameras that harvest for us data in real time and try to control autonomously the intersection, the traffic lights. Now, what is the state of the art there? The state of the art is either, as you know, timed traffic lights. So they effectively are there for 15, 30 seconds, and then they switch from red to green. Or the big fuss that you've heard here in Cyprus, the smart traffic lights in Limassol. These are magnetic coils that they rely on magnetic coil sensors that are buried underneath the road and are metal detectors. That's all they are. They count cars in a very noisy way, but they do. They count cars. So they try to adaptively give priority to the busier side of the road. It's a very expensive way and not very efficient. What we're looking for is a fully adaptive end-to-end trained signal control system. Our system operates only on pixels, so we just pass it the camera, what the camera sees, and it optimizes traffic lights directly. So this is the state of the art that we've already talked about. There have been deep reinforcement learning techniques in the past, but they were not doing it on CCTV. They were doing it on what you see here is some pretty rudimentary simulation. So this is the sort of image. This is the sort of image that we operate upon. This is Transport for London cameras that are already there. We haven't installed. We have nothing to do with. And we get information that's much richer than what the magnetic induction loops give us. What's more important is that we don't do any recognition or segmentation of the image or anything like that. We just throw it like it is, the raw pixels. This is quite important. People are concerned about privacy. We don't want to really understand what's going on there. But even more important than this, it turns out that our system does much more than just count vehicles in order to do the optimization. So the process is what you see there. We harvest the images in real time. We pass them on to our agent with deep reinforcement learning, again, trying to maximize cumulative sum of rewards, explores different states to gain the rewards, and control the traffic light, then observe again, and so on. So this is here your standard loop for deep reinforcement learning. These are the different actions you have at your disposal. The state is not handcrafted anymore. The state is the raw pixels. The rewards are handcrafted. Very simple. We just give a reward of +1 if a vehicle passes, and -1 if it waits. And then later on, when we want to deal with emergency vehicles, we give +5 for emergency vehicles, or -5 if we don't let them pass, if we have them wait. So this autonomous signal control is based on policy-based deep reinforcement learning. we compute the gradients, having explored actions, and update the policy. This is what the architecture of our system looks like from raw pixels to action. The action, sometimes people get confused. The action is not red or green. The action is rather what you see here, the allowable combinations. How does that do? Let's have a look. What you see there on the graph, the y-axis is how long it takes to traverse the junction. The x-axis is the experience of the agent, how many vehicles it has seen before. And the blue is your regular fixed time signal control. The green is the one with the adaptive, the magnetic loops that does vehicle counting with some. Here, actually, it doesn't have noise. In real life, it has noise. Here, it's the adaptive is noiseless. It's its best possible case. With the darkest red, the maroon, you see the performance of a policy gradient deep reinforcement learning agent that doesn't operate on CCTV, but on vehicle counts. And the bright red is ours. And you see how quickly it converges to a substantially better performance than all the rest. So this has been very encouraging, but where it really shines is, in comparison to all the other approaches, is when the traffic varies. So the graph that you see on the left is the same as you were seeing once everything has converged, pretty much. On the right, the traffic is no longer uniform, the traffic constantly changes. So it could be this stream that's really busy, and then the next 2 minutes is this other stream, and then the next 2 minutes is both streams really busy, and so on. Our performance is substantially less than everything else. It's again the bright red. You want it to be as little as possible. The y-axis, I remind you, is the junction traversal time. So having seen these good results, we want to see, is it really possible to transfer it to real intersections, and what does it take? We want to make sure that this good performance continues across different topologies of junctions, different weathers now, because we're depending on visual cues, visual sensors. What happens at night? Does it still work? And remember, it's a system where the agent learns the essential features on its own. We don't tell it, this is a vehicle, or this is a bus, or this is an emergency vehicle, do prioritize it. It learns through the rewards. So a lot of it lies in the art of training and domain randomization. So you see there, this graphical simulation environment is something that we built. It's called Traffic 3D, where we can control both the behavior of the vehicles, we can control the weather, and so on. If you bear with me on this one, I'm going to cover it in a few slides when we talk about simulation. But I want to show you, having been trained in that environment, how well our system performs, how easily we can deploy. So here, what I'm showing is in a system which has been trained only with treating all vehicles the same, we suddenly start giving it more rewards for prioritizing emergency vehicles. And the difference here, the blue line is what I've just told you. The red is with transfer, and you see how we can employ transfer learning to learn much faster. And here I'm showing you performance with different weather. So having been trained on a sunny day, if I throw it on a dimly lit night, if I throw it in a situation with heavy rain, how well it adapts. And in fact, its previous training from just a sunny day, it makes it do better than just being trained on rain or just being trained on night. And this is being deployed to a new junction layout. When I deployed with the blue, just training on the new layout, it does fairly well. But when it's been trained on other junction layouts and with the red, and it sees this one, having seen other junction layouts, it initially does worse, but it achieves very quickly a much better result. Now, this wasn't enough. We wanted to see its deep learning, and you always have this thinking of, but why does it work? What is it that it's looking? So we did some visualization of the final convolutional layer, which generates a heat map that we overlay over the input image. So with red, you see where the attention effectively is. So you see, can we see the image? Yeah. So you see here the reds in the bus because we are giving high rewards for the buses. You see here in the red the longest queue. Again, the buses here, the buses, what I really like to show is this is a pretty rubbish image where it's raining. The raindrops have gone on the camera lens, yet it still prioritizes this bus. It works in the dark. It works when you have the lights on a wet surface. So this work, with the help of the media, has really gotten the attention of the policymakers. So at the moment, we are deploying a trial in Coventry, and this is the first AI trial in the space of traffic that anybody that I've spoken to knows about. So we're really proud about that. We've got 3 junctions fitted all with cameras, and our cameras cost, we had some budget to burn, and we bought the most expensive cameras, and they're only 3K. In comparison to the magnets that they need to bury under the road, which cost about 150K just to buy, let alone install and so on. So this is an exciting piece of work that I'm hoping I'll be able to report more in the future from this trial on the roads. The final bit of work that I want to talk to you about is simulation and digital twins. This is a very strong area in the area of agent and multi-agent systems, and traditionally it's been used a lot for policy making. So let's make a digital twin of a market, let's make a digital twin of a society to try and understand which are the interactions that drive the behaviors that we see, how can we influence the behaviors, and so on. And I've done that a lot. I've collaborated with the government, with the Home Office to do immigration policy of high-skilled workers. So in the UK, they're very keen, for example, in attracting doctors. But doctors, when they come and they're trained by the NHS, they become highly valuable, and they're then snapped up by Australia or Canada. And they wanted to look at what law they could put in or what incentives they could give to those people to not leave the UK, having made the effort to bring them from Asia and retraining them and so on. I've worked a lot in civil unrest, again with the Home Office, and also trying to understand consumer attitudes toward fair trade products with the Department of Business Innovation and Skills. But increasingly, I find myself using agent-based models and deploy them in totally different settings. Sometimes to elicit data, sometimes to synthesize data for our machine learning, sometimes as training grounds for our agents, like the traffic light agents that we have here. And this is a very exciting project where I'm working with a set of psychologists and nutritionists that want to find out how children learn what to eat and what not to eat, how to get children to eat more vegetables and so on. And they believe that it's a lot to do with the setting where the food is offered, with what the parent says, what the parent does at the same time, and so on. And their problem is that the parent won't always admit or won't always realize the way they're handling the scenario. So a questionnaire or an interview, which is their normal approach, doesn't really work. So this here is what looks like a game where the parent interacts with a child that they customize to look like theirs, that they customize to have the same personality as theirs, and so on. And they're offering food to the child in particular settings, in front of the TV, with an iPad, without an iPad, with the family there eating their broccoli or whatever it is. But the cool part from the science side of things is that the child is learning with the reinforcement learning. The parent doesn't necessarily know that. And this is really at the cutting edge of research, and I hope to be able to come back and let you know more on this front. So this is a fairly new project. And of course, I have some students generating new game scenes using GANs and so on. So that's one with high potential. No results yet to show you, but I wanted to share with you this area. And of course, I really need to talk to you about our simulation of traffic because it's really at the forefront of what's happening right now. There are many established tools for simulating traffic, yet if we're going to be using cameras as sensors to help us make decisions, we need to have our agents trained in environments that are close to photorealistic. So we've been creating this simulator that simulates both the behavior. It also has the precise physics of movements in a game environment, which normally is not present in your normal transims, vsims, which are the state of the art. And it has a lot of photorealism. I'll tell you what it looks like. I'll show you what it looks like. And it's totally customizable. For us, it's important that you can control the weather so that you can obtain the images that you need for the training and the domain randomization, which is what makes, in my opinion, and as I see now at the trial at Coventry, what makes the efficiency of our agent. This is, you see the camera gets the raindrops and so on. And I think, yeah, we have snow and we have the night shadows and so on. And the results I've shown you for the traffic control agent are based on the training that we've received here. However, it's been nagging me that there's always a big gap between simulation and the real world, and photorealism is hard, but at the same time, all our models still lack fidelity. If you've driven in another country, you know that the driving behavior is different. Even within the same country, having moved from London to Cambridge, then to Birmingham, the driving behavior is completely different. Cambridge is geriatric, Birmingham is the Middle East, and they're only 100 miles away. How can I then be confident in the traffic models that traffic engineers use when I know as a person who works in simulation that the slightest change in initial conditions causes a big difference in the properties of the system that I observe. So the idea that we had is how can we use footage, CCTV footage from specific junctions to inject realism to our simulators. So when I talk about realism, I mean two things. I mean photorealism, and I also mean fidelity of the driving behavior. So what we've been doing here, we've been using graphical neural networks, generative modeling to extract the vehicle positions, the time of day, the weather conditions, and a few other features from real-time, not real-time in this case, from video to use this graph to condition a generative neural model and regenerate, synthesize a simulation that works in the same way. And then I can do fancy things. I can generate a simulation with that particular those particular surroundings, but vehicles of my choice. Here I chose only to generate white cars because I wanted to show you I can. Daytime, or nighttime, and you see the lighting is nice. I'll show you on the left-hand side is the real footage. On the right-hand side is the generated one, the synthesized one. You see it a little bit jittery. It's because our PhD student wanted to submit. All he needed was to create bigger bounding boxes. I can, what I'm showing you here, and this is, I think, one of my last couple of slides, is how I can generate the setting. So I'm showing on the left-hand side where to place the cars, and they are placed, what color they should be. So here I'm drawing a little rectangle, and that's where the vehicle appears. And then we can change the time of day, and it will behave the same way. This is a Russian junction, the same way that we've seen it behave in the vehicle. So we measure things like acceleration, deceleration, space left between vehicles when stopped, and so on. And this compares, nobody else does that. And we're able to mimic what we see. Our industrial network was immediately drawn to that. So we've recently, we got this project with Agilicis to use our simulation tool in order to predict what traffic is going to look like in areas where we only have partial sensors. So if we have, let's say, vehicle counting sensors or air quality sensors, can we create a simulation of what traffic is like? Or if we have CCTVs, can we predict from that what the air quality is going to be like? And so that was 260,000 and 360,000 is the new project that we just got a couple of weeks ago with Smart Transport Hub, which we're going to be going around with a vehicle all kitted out like the Google vehicle. And we have already a simulation that's going to be updated by what the sensors of that vehicle pick up. So for example, there's a school there, we know, but the kids come out of a particular area and they use this particular space and so on. The kids use this particular space and they gather and maybe they need, let's say, benches or something like that. So this is what I've covered today. We've talked about mechanism design. I've given you the example of supply chains. We've talked about real-time learning and transferring learning that we've acquired in the past, both in the energy trading competition and our traffic management agent that we're deploying in Coventry at the moment. And we've also talked about simulation. For me, my passion is to see my research applied. And whatever it is we're doing, supply chains or traffic or simulation or energy usage modeling, I'm proud to say that I'm seeing my work being deployed both in the government and in the industrial sector. And that's it. Thank you very much for bearing with me through the technical problems, and I'm happy to take any questions. I'll hold the microphone.
I'd like to thank you for the seminar. And I have two questions for you. So are there any hidden costs associated with running these models all the time, 24/7, I assume? And are pedestrians actually included in the...
Thank you. I forgot to say that. Thank you for reminding me. Yes, there are. So I'll start with the second one. So pedestrians, gosh, I can't believe I forgot that. Pedestrians are involved. What we call vulnerable road users are involved. So pedestrians, cyclists, scooters, and also people in wheelchairs. So in optimizing, I've shown you here the Where am I? So we are optimizing for whatever the traffic lights are going to show. So what you see on the right-hand side, but without explicitly recognizing what it is, just by giving your system rewards. If you want to prioritize pedestrians, this is the beauty of our systems. I can't believe I haven't told you. The beauty of our system is that you can deploy it near a school and tell it to optimize for pedestrians. You can deploy it near a work site and tell it to optimize for trucks. It doesn't explicitly recognize them. It learns to optimize through the rewards that you give it. But yes, the short answer is yes, it works for all types of road users. Hidden costs around computation. Not that much. So in any case, not comparable with the cost of buying and installing the magnetic coils. We are deploying, as I said, now in Coventry, and our computation is pretty inexpensive still. In fact, we had planned for some local computation, but we are also going to test for sending our data over Wi-Fi. And check how that works in terms both of performance and of cost. So it's doable to do both ways. If you can afford to send your data over Wi-Fi, your computation really cannot be that much. Thank you for the questions.
Hello, thank you for the great talk. My question is also about pedestrians. You said that your input to these models is just a pixel by pixel. How do you incorporate the buttons for crosswalks for pedestrians?
How do I incorporate?
The crosswalks that pedestrians use to cross the road. You know, you press a button and all the...
We don't. We could, but we don't. So we assume that somebody, well, we don't assume anything. We just pass it the picture. But any object that's waiting is counted as waiting. So if you have pedestrians waiting, your system is going to get negative rewards. So it's going to learn to prioritize them. We can make it much easier if we incorporate the Pelican crossing, which involves a button. Interestingly, I had a couple of bus companies, you know, it's all privatized in the UK, come to me and said, if you can do this for pedestrians, can we incorporate it at bus stops and dispatch buses based on how many people are waiting at the bus stop? And this is quite important because you have your day-to-day use and demand that companies probably know about, but then you have the unexpected. What happens if there's a big football game, or what happens if there's a big concert and there's an increased demand? What happens if the trains are down, so people are having to use the bus? So they're really interested in deploying this sort of technology to pick up additional demand and affect their bus schedules.
When you said about let's say that is a football match, can you optimize the actions to prioritize, let's say, pedestrians using the underground instead of traffic? So, you know, there are not many pedestrians waiting.
Are you talking about routing people?
Yeah.
Thank you. You're asking all the right questions. It's like I've planted you, really. So this is a project we're currently bidding for, not so much for pedestrians, but this brings together mechanism design that I've talked to you about and online learning. So the question is, can I advise some of my traffic to take a particular route to ease the traffic in a particular area? And the answer is, you can do anything you want, but will the people comply? People are intelligent, autonomous agents themselves. And the counter answer there is, well, they would comply if you gave them incentives. So what sort of incentives can you give to this person who's going to the concert. You're telling them, take the longest route. Trust me, it's going to be better. Is it going to be better for them, or is it going to be better for everyone else? So it's a matter of what incentives do you offer if somebody can then show that they followed the route. Waze, which is the company behind Google, are really interested in that, and they've been talking to us. And we're looking at maybe, let's say, discount at some merchandise offered at the concert, or discount for your next concert if you follow the rule. This is the sort of monetary incentives. But what incentives are going to be good enough in order to achieve that? And in a related project, which we're currently working on, we're looking at, the main project is really about where to place charging stations for electric vehicles. Where in the network, there are different types of chargers with different costs and so on. What incentives do you give people to take particular routes that are going to need particular chargers in order to optimize load in the network? And this is associated with then the cost of the energy that you're going to buy and so on. And what's a good incentive, what's a not so good incentive, and so on.
Thank you.
Thank you.
Thank you very much. It was very, very exciting. So I'm not expert in the field, so more from, let's say, scientific curiosity. So as you also mentioned, most of the systems are in principle chaotic.
Yes.
So did you consider any methods for uncertainty quantification of your predictions? For example, providing uncertainty quantification, for example, Bayesian-based methods or other?
Yes. So I've worked a little bit in that in the past, where from a slightly different angle, we were trying to do emulation of our systems to make them run faster, to be able to run them in mobile phones for decision making and so on. And for that, we employed Gaussian processes as emulators, and we had to run many instances of our simulations in order to be able to get those error bars, if you want, around them, and also to see where we're really off what we were expecting.
You apply this method?
Not to this one, but this is currently ongoing. It is in fact just starting, the traffic one, but it's in the plan. Yes.
Maybe one more. At some point, we mentioned about your simulator that we include, let's say, physics-based information.
Yes.
Can you elaborate a bit more on that? So do
Yes.
you combine this with the neural networks?
So what we do there is really taking into account the weight of the vehicle, how it's going to swerve based on its weight and its velocity and so on as it turns and so on. So this comes from the game engine, which has those models inside incorporated. We don't do anything specifically with machine learning on the physics in that part. This would be a very interesting, when we talked before and you mentioned physics-based, I thought that'd be a really good idea to go in that direction. Thanks. Guys, thank you very, very much for having me here. It's been really nice. Thank you.
Thank you. Thank you, Professor Maria. We can continue our conversation outside with snacks and juice.
Thank you very much.